Welcome to the wonderful world of analysis. In this video, we're going to look over a few theorems and some definitions from sequences. So the first theorem we're going to look at is something called the Bolzano-Weierstrass theorem, named for two mathematicians, Bolzano and Weierstrass. And what the Bolzano-Weierstrass theorem tells us is every sequence in a compact metric space X has a convergent subsequence. Okay, so this is an important theorem. It has applications in mathematics, certainly, and even has applications in fields like economics. Before we go into the proof, I would put out a warning that this does not immediately apply to the real numbers, because the real numbers are not, in general, a compact metric space. The compact is very important. So let's look at the proof here. So recall that we're defining a sequence to be a function from the natural numbers to our metric space X, where the nth entry is the image of the integer n. So we're going to consider two different cases here. Either the range of f is an infinite set or a finite set. So let's start with a finite set. So if the range of function, that is all the points in our sequence, is a finite set, what we're going to do is then we're going to say then there exists, let's call it a P in this range E, such that f of k is equal to P for infinitely many k. So let's think about why that should be. We have infinitely many integers. The range is a finite set. This is just the pigeonhole principle used again and again and again. Okay, so then if we look at the inverse image of this one point P, what it's going to do is it's going to have infinitely many points in it. So let's say it has nk1 and nk2 and so on. We can put nk3, nk4. It will keep going forever. And in fact, we can go ahead and we can order these. We can say nk1 is strictly less than nk2, is strictly less than nk3, and so on. Having these indices ordered in this way, this defines a subsequence. All right, so this defines, let's call it a subsequence P and K with P and K converging to P. Now that's actually fairly easy to see the convergence because every entry in this subsequence is exactly P. Okay, so since P sub nk is equal to P for each k, we can certainly make P sub nk minus P less than any positive number epsilon. Okay, so that takes care of the finite case. We've built it pretty nicely here. On the other hand, we need to look at what happens if E is an infinite set. Okay, here we really need to take advantage of the fact that our hypothesis is X is a compact set, or compact metric space. Since X is compact, what we have is there is a theorem in our book, Theorem 2.37, guarantees us that there exists a P in X that is a limit point of our set E. Now I would note here the suggestive name limit point. Okay, well, limit point, that means we can put neighborhoods around it. We're going to always have an element of our set E. Okay, so let's take a neighborhood with radius 1. So n, a neighborhood of P with radius 1, if we intersect that with E, it's not empty, okay, by definition. So we're going to now select one element, let's say P sub n1, in this neighborhood. N1 of P intersect E. So we're going to start building our sequence. We have one element of it. Okay. Then what we're going to do is we'll just take a smaller radius. We'll look at n1/2 P, neighborhood of radius 1/2. We intersect that with our set E. Again, it is non-empty, definition of a limit point. So we can select, let's call it P sub n2 in this neighborhood intersect E. All right, now we're just going to continue. Okay, just keep going, keep going. We're going to keep selecting more points. We're going to select, let's say, P sub nk in the neighborhood of radius 1 over k, P intersect E, and what we've done is we've formed a sequence. Okay, this is again not empty. Then our subsequence, P sub nk, converges to P. Now, I could prove this pretty nicely. Like any good analysis proof, let's start with given an epsilon greater than 0, our Archimedean property. Very, very important property. We use it all the time, especially here in sequences and series. Our Archimedean property says there exists a natural number, let's call it m, in the natural numbers, such that, well, what I can get here is 0 is less than 1 over m is less than epsilon. Now really for the Archimedean property, I have found a number m such that m times epsilon is greater than 1. Okay, but a little algebraic rearrangement, I can get to this. Then the distance, this is again with respect to our metric, from P sub nk to P is less than 1 over k, that's how we've been selecting things, which is going to be less than or equal to 1 over m, which is less than epsilon, as long as I go out far enough in the sequence for all k greater than or equal to m. Okay, and that finishes up our theorem. We had two cases, either our set was infinite or finite, and we were able to prove it in either one. Now an important thing I would note here, this is an analysis theorem, it tells us that such a point exists. Okay, we've proven that we have a convergent subsequence. It did not tell us what this convergent subsequence is. We do not have an explicit here is this subsequence P sub nk. It does not tell us what this limit point P is. It only tells us that they exist. And for a lot of applications, a lot of things we need to do, that is going to be enough. So let's see what else we can do here. Well, a very important definition we're going to work with is something called a Cauchy sequence. We're going to say a sequence in a metric space is called a Cauchy sequence if for all epsilon greater than 0 there exists a natural number n, so the distance between P sub n and P sub m is greater than epsilon for all m and n greater than or equal to this capital N. Well, let's think about what this is trying to tell us. This is basically saying the entries of our sequence are going to get arbitrarily close as long as you let us go out far enough in that sequence. So far enough here would be dictated by the natural number capital N, and close enough is going to be dictated by this epsilon greater than 0. Okay, so let's see an example of a Cauchy sequence. Let's just start with a very simple sequence. Let's start with 1 over n. And we'll just go in our standard real numbers with the standard metric. So before we get into actually showing this, let's just do a little algebra on the side here ahead of time. Let's look at 1 over n minus 1 over, let's say, n plus k. Okay. If I put this together on a common denominator, I'll get what? N plus k minus n over n times n plus k for a grand total of, let's see, we'll have k on top and n squared plus k times n on the bottom. Now, in analysis, I want to make things bigger. Right, I want to bound above by an epsilon at the end of the day, so I could make this bigger by getting rid of something positive on the bottom. The bottom's all positive, so n squared plus kn is definitely bigger than kn, so this is less than or equal to k over kn, which is 1 over n, which is certainly less than 1 over 2n. Right, because n and k are natural numbers, this I can definitely do. Okay, so let's prove that this is a Cauchy sequence. To prove it for all epsilon greater than 0, we can't do that in one fell swoop. We have to start with an arbitrary epsilon greater than 0. Again, by our Archimedean property, going to invoke this an awful lot. Pretty much every sequence we prove, we're going to invoke this. There exists, let's call it a natural number, capital N, such that n is greater than 1 over 2 epsilon. Okay, then if I take an m and an n greater than or equal to capital N, okay, and without loss of generality here, I'm just going to assume that m is bigger than n, so it's n plus k for some natural number k. Okay, obviously if k is 0, their difference is 0. We don't need to worry so much about that. So if I have that, then I can look at this 1 over n minus 1 over m. This is my distance from P sub n to P sub m. This is, by the algebra we did up there, less than 1 over 2n, which is certainly less than or equal to 1 over 2 kn capital N, since I've taken m and n greater than or equal to capital N, which is less than 1 over 2. If I make the bottom smaller, I make the whole thing bigger, and n is bigger than 1 over 2 epsilon, so I can insert that 1 over 2 epsilon in there. And now, just like magic, these 2's cancel out, the epsilon comes to the top. This is less than epsilon as desired. So we have a Cauchy sequence. Okay. Another definition that's quite important is something that's called the diameter of a set. So we're going to take a metric space X and a non-empty set E inside our metric space. Now I'm going to take a collection of real numbers. Real numbers are great because they have the least upper bound property, lots of very nice properties we can take advantage of. So I'm going to let S be the set of distances from P to Q over all P and Q in our set E. Okay, this is going to be a subset of the positive real numbers. Might be 0 if this is 1 point, but no negative numbers, just positive numbers and 0. The supremum of the set S is called the diameter, and this is really, it's a generalization of the diameter of a circle, really, if you think about it. Because if I had my set was a circle, you know, the farthest apart is going to be right across the diameter. So this is the idea. We're going to look at something called the diameter. So let's just look at an example of this. Let's consider the set, the open interval 0 to 5 in R. Okay. Now obviously, if I think about this, I start looking at points. I mean, down here at 0, up here at 5. The biggest I can get is that I get arbitrarily close to 0 for P and arbitrarily close to Q, or to 5 for Q. I can see that this diameter should be 5, at least under the standard metric. Now, of course, the metric here is underlying it is very, very important. If I use the discrete metric, now we all remember the discrete metric from our homework. The discrete metric said the distance from P to Q takes one of two values. It is 1 if P is not equal to Q, and it is 0 if P is equal to Q. Now, under the discrete metric, the diameter of E, it can't be 5, it's 1. Because if I take any 2 points that aren't equal in my set, the distance is 1, so my set S is consisting only of 0s and 1s. The supremum of that set is 1. Okay, so now we are ready to prove a final theorem here. The theorem says if X is a metric space and E is a subset of our space X, then the diameter of the closure of E is equal to the diameter of E. Okay. Now, before we go too crazy, let's think about why this should be true. Now, the intuition behind this is if I take, let me just jot something down here, for all X in the closure of E. Now, if I'm in the closure, that's either E or I'm a limit point, okay? Because the closure is E union its limit points. Now, if I take any X in there, if it's in E, right, then I'm in E, there's no problem. But there exists, for either case, a y in E, y could be equal to x, arbitrarily close. And arbitrarily close, that's generally with our epsilon. So since I can get arbitrarily close, the diameter of E bar can't be too much larger. All right, it can't be larger than the diameter of E. Okay, this is the idea. This is what this theorem is telling us. Okay. Now we know that in analysis it's hard to prove directly that two things are equal. We've run into this problem many, many times. Now in our first homework we proved the very, very handy fact that A is equal to B if and only if the absolute value of A minus B is less than epsilon for all epsilon greater than 0. Now this, of course, we did for the absolute value. That was our first example of a metric before we were talking about metrics. But in metric spaces we can replace that absolute value with the metric. Okay. So first of all, let's figure out what to do. So E is a subset of E bar, the closure. So the diameter of E has to be less than or equal to the diameter of E bar because the sets we're looking at, we're taking a supremum over a set of distances. When we go from E to E bar, we're adding in more points to look at. The supremum is only going to increase. Okay, so really all we need to show now is that the diameter of E is greater than or equal to the diameter of E bar. If we can do that, we're going to be in good shape. Okay, so we're going to start a nice analysis proof here. Given an epsilon greater than 0, we do want to prove something for all epsilon greater than 0, so we're going to start with an arbitrary epsilon greater than 0, and we're going to take some arbitrary points P and Q in the closure of E. Now since it's in the closure, either P and Q are in E or they're limit points. So we can get, without working too hard, by the definition of limit points, there exists P prime and Q prime in E, so that the distance from P to P prime is less than epsilon over 2, and the distance from Q to Q prime is also less than epsilon over 2. Okay? And now I'm going to start looking at the distance from P to Q. And this was just 2 arbitrary points. Okay? Now this, by our triangle inequality, I can say this is less than or equal to the distance from P to P prime plus the distance from P prime to Q. Okay, I just put a P prime along the way. The triangle inequality allows me to do that. And now I'm going to use the triangle inequality one more time on this second piece. This is definitely less than or equal to the distance from P to P prime. Not going to mess with that. Plus the distance from P prime to Q prime plus the distance from Q prime to Q. Okay, so now let's see what I've got here. I know by the triangle inequality this piece right here, this is smaller than epsilon over 2, and this piece is smaller than epsilon over 2. So what I have here is the distance from P to Q is less than, strictly less than, epsilon plus the distance from P prime to Q prime. Now the diameter is the supremum over these distances, so if I have a distance between 2 points in E, this has got to be less than or equal to epsilon plus my diameter of E. Okay, so let's see what we have here. This is definitely going to hold because I picked things arbitrarily. This is true for all P and Q in E bar and all epsilon greater than 0. So this tells me I can take this and look at this. This is true for all P and Q in E bar. So if I take the supremum, it's going to be true. I've got the diameter of E bar is now less than epsilon plus the diameter of E. Okay, and this is true for all epsilon greater than 0. So this tells me that the diameter of E bar minus the diameter of E is less than epsilon. Now this I know has to be a positive thing, okay, because at the start we started with the diameter of E bar is bigger. This is true for all epsilon greater than 0. So this is basically telling us we can insert absolute values in here. We can conclude the diameter of E bar has to be equal to the diameter of E as desired. And that's what we were trying to prove. And now from here we can actually prove quite a number of interesting things which we're going to do in class.